Okay, so we've been talking about chemical reactions now for quite some time. And up to this point, we've been sort of thinking about chemical reactions like, let me write this out. A plus B produces C, let's say, plus D, a little bit smaller of a marker. We have been talking about reactions like this, and we're sort of just figuring that A and B are always going to be producing C and D. But it's important to appreciate that some reactions are really quite fast, and some are slow. So in order for us to appreciate this, we're going to make a bunch of measurements, and we're going to introduce some language, and we're going to call this domain kinetics. Okay, so this is the rates of reaction, and we're going to find pretty clever ways, I think, that are going to fit pretty nicely in your head with respect to how we describe these reactions and measurements we do, calculations we do therewith. So let's look here more. The rate of a reaction is the change in the amount of a reactant or product per unit time, right? So it'd be the change in a reactant. So I might do that, A per unit time. Let me say per second, right? So the change in A per second. It's often convenient to express this amount in terms of concentrations. So I might say, do I have this right? Yeah, let's go here. I might say the concentration, the change in the concentration of A per unit time, right? So the rate expression now is the mathematical representation of the rate of the reaction. So we might say the rate is equal to, let's say since A was one of the reactants, it would be disappearing. We might say minus the change in the concentration of A per second, right? That would be a good way to describe the rate of the reaction that I had on the previous page. Okay, so reaction rates are always positive. Let me write that again. The rate is equal to minus delta, the change in the concentration of A per, let's say, per second. Okay, that would be one way of writing it. These are always positive quantities, right? Because if A is a reactant, it's losing, so that number is going to be negative. The change, this number is going to be negative because that's the change, right? That would be the concentration of A2 minus the concentration of A1. And so if A is disappearing, we might find it, let's say A might go to 0 if it completely disappears, and it might start out, let's say, at 1 molar, right? So if it ends up with 0 and it starts out at 1 molar, then you can see that's negative, right? So we might say the negative of the negative, and that's because we want to express rates as positive quantities. Concentration is usually expressed in terms of molarity, and notice I said that when I was saying 0 and 1 molar, right? So we're typically going to say molarity. We can also do this in terms of partial pressures. Rate expressions can be written in terms of a reactant or product concentration, which is what I said here. If in the previous reaction A plus B produces C plus D, we might say this rate is also the rate of the appearance, that's positive, of C per second, right? Well, that's meant to be a delta. It's a pretty ugly delta, isn't it? Let me change that. That was a little bit ugly. Let me do that again. Delta C, right? And that would be the same as the disappearance of a reactant because this is a product, right? Okay, so now let's practice this. Let's write the rate expression in terms of each species. The rate of N2O5 decomposition is going to be minus the change in the concentration. Oh, this is a gas. Oops. Well, we could do concentrations. Gases are written like that. Let's do it as concentration right now, because if you've got a vessel and you've got a gas in here, this could be 1 liter, and you might have 1 mole in there, right? If you've got 1 mole in there and it's 1 liter vessel, you'd say it was 1 molar of gas, 1 molar gas, right? So we could say N2O5, right, per second, right? Or we could talk about the rate of NO2 formation, in which case we would say delta, because this is actually getting higher, so this is going to be positive, NO2 per second, right? Or the rate of oxygen formation could be delta, the concentration of oxygen per second, right? Okay. Now, just a second here. Okay. So the average reaction rate is the rate which a reaction occurs over a particular time period, right? So the average reaction rate from the beginning of a reaction might be from time is equal to 0 to time is equal to 30 seconds, right? And we would take the concentration at time 0 and the concentration at time 30 seconds, and that would be the average rate. We'd take the difference, right? That would be the average rate. But the instantaneous rate now, the instantaneous rate, that's the rate at any particular moment in time, that would be the rate at which a reaction is proceeding at a specific moment in time, right? So in order to do that, we use a graph of concentration versus time, and we find the slope of the tangent line. Okay, we'll do this in the next slide. The tangent line is the line that's touching at that particular point. And we can also determine the average reaction rate over a very, very short period of time, which we will call, if it's short enough, we can call it instantaneous. Okay, the initial reaction rate, of course, is the instantaneous reaction rate at time 0. So let's look at these in a graph. So in a graph, we might say, what is what is that, 11 hours? Maybe this is 11 hours, okay? So the instantaneous rate at 11 hours would be, we go to 11 hours, right there, and we say, all right, let's draw a tangent line at that point. So we draw the tangent line and we find the slope of that tangent line, right? So to find the slope, we just do rise over run, right? Can you see that? So this might be 17 seconds, or hours, hours. And this might be what, 4 hours? 4 hours, right? So the change in time is equal to 13 hours, and the change in concentration might be, I don't know what that is, 0.48. Is that right? Let's do that. 0.48, it's not quite 0.5. And the concentration here might be, I don't know, 0.18, right? I'm looking at the concentration here. Concentration of H2O2, right? And so the difference in these two concentrations, concentration is equal to this, the difference between these two might be 0.18 minus 0.48. That would be 0.30, right? So here's my rate. It would be negative, right, because it's going down. So I'd say my rate would be negative 0.30 divided by 13 hours, okay? So the instantaneous rate, again, is the slope of the line, the tangent line. The initial reaction rate is the tangent here, right? So you would just take the tangent there. And the average would be, the average for the first, let's say, 18 hours. Let me change my colors here. The average for the first 18 hours might be, right, that to this, right? So you take that, you take those 2 points right there, and you find the slope of that line, and that is going to be the average rate for the first 18 hours, okay? So the rate of a reaction may be expressed in terms of a change in concentration over time. Stoichiometric factors derived from a balanced equation may be used to relate reaction rates. For example, if the rate of NO2 in a previous example, the rate in terms of NO2 was, I think it was producing NO2, so it would be the change in the concentration of NO2 per second, right? But the rate of the reaction, forget what NO2 was. Let's go back up here. NO2, it was 4, right? So the rate of the reaction is going to be 1/4 of that. And we'll practice that. That'll make a lot more sense as time goes on. But the rate of the reaction is going to be 1/4, right? You take the stoichiometric coefficient, which is what this is saying here. Stoichiometric coefficient, NO2 over seconds, right? That's the rate of the reaction. The rate of the NO2 is going to be here, but the rate of the reaction would be the NO2 divided by 4 because the stoichiometric coefficient is 4. We're going to need to practice that, I think, before you're going to really appreciate that, before it's going to seem simple. All right, good luck.